We typically imagine space exploration through the lens of human astronauts planting flags and leaving boots in the lunar dust. But the modern reality consists of a quiet fleet of isolated machines operating in the dark. For decades, these robotic explorers were essentially driven on a long leash. Spacecraft relied entirely on either direct human piloting from within the capsule or real-time remote control from engineers back on Earth. That method breaks down once you travel deep enough into the solar system. The physical distances are simply too vast. Even at the speed of light, a radio signal can take over 20 minutes to cross the gap between Earth and Mars. That communication delay creates a fatal lag. If a rover on the Martian surface is driving toward a steep crater, the ground team won't see the danger until 20 minutes after the hazard appears. By the time Earth issues an emergency stop command, the vehicle has already fallen in. Pacing speeds up. To survive these hostile environments, spacecraft have to stop waiting for instructions. They need to analyze their surroundings and make their own instant decisions. The harsh physics of the universe dictates a strict rule. If we want to explore deeper into space, we have to let go of the steering wheel and give our machines autonomy. NASA's Perseverance rover is the definitive proof of autonomous exploration. It crawls across the Martian landscape, driving itself 88% of the time. In 2026, the rover completed a 2-day, 456-meter drive entirely on its own. It generated its own navigational waypoints without a single directional input from mission control. By combining LiDAR sensors with edge computing, the rover processes data internally rather than beaming it to Earth. It builds a geometric map and instantly flags a crater as a hazard zone. Without asking Earth for permission, it calculates the safest path around the obstacle. This autonomy extends beyond ground rovers and straight into Earth orbit. Satellites like InnoCube are now actively adjusting their own orientation and stabilizing themselves in a vacuum without any human input. Back on the ground, private companies like Rocket Lab use similar intelligence systems for predictive maintenance. By analyzing the massive datasets generated on the manufacturing floor, algorithms catch microscopic component anomalies before a rocket even reaches the launch pad. Artificial intelligence has become the foundational operating system of modern space engineering, providing the real-time logic necessary to keep these missions alive. Sending machines instead of humans offers undeniable logistical advantages. It drops the mission cost dramatically, entirely eliminates the risk to human life, and allows the explorer to enter lethal environments with zero hesitation. Machines also synthesize information on a scale we cannot match. When telescopes and interplanetary sensors flood us with enormous volumes of telemetry, AI can instantly classify celestial objects and pull out subtle anomalies that a human eye would naturally gloss over. But these systems carry their own severe vulnerabilities. Spacecraft have limited onboard computing power. If an algorithm encounters a situation outside its training data, it can make fatal errors without any human oversight to hit the brakes. This is where human intellect still holds the absolute advantage. A human brain possesses lateral thinking and the capacity for sudden innovation. Confronted with an unknown anomaly, a trained astronaut can adapt their approach on the fly. Ultimately, neither entity is a perfect explorer in isolation. The machine is permanently bound by the rigid limits of its code, while the human is constrained by the fragility of their biology. Because of this, upcoming endeavors like the Artemis II lunar mission are not designed as a competition between humans and algorithms. They are built as a strict symbiosis. The mission divides the labor based on strengths. The AI systems are assigned the immediate survival logistics, managing autonomous diagnostics, avoiding lethal hazards, and executing orbital traffic coordination. By delegating these rapid-fire calculations to the machine, human astronauts are finally freed from the overwhelming mechanics of flying the ship. They can dedicate their entire focus to high-level scientific discovery and complex decision-making. But looking further down the timeline, a question emerges. As we push deeper into the void, there will come a point where human physical endurance simply maxes out, while the capabilities of artificial intelligence continue to scale up. Our primary role in the universe is shifting. Instead of always providing the boots on the ground, we are becoming the architects. We are designing the minds that will go out and do the exploring for us. The enduring legacy of our human species may well be the artificial intelligence we have unleashed into the cosmos.